It's the same function. You're asked to graph the results, the resulting series on the same interval. One of them is sine, the other one is cosine. I told you we don't always try to get too imaginative in creating things. The function stayed almost the same. We changed the interval next time. It's about time to change the function. That I'll say. And I do say that seriously. It's about time to change the function. So the function you will get is not f of x equal x. But I'm going to do one of these. And on the other hand, it kind of alternates between cosine and sine. So what, do you want me to do cosine or sine?
Do both.
Both?
Whichever one is on
Oh, isn't it?
Cosine. Do cosine.
Cosine.
Do cosine.
Do the one that'll be on the test.
Huh?
Do the one that'll be on the test.
That's why I asked you to choose.
Sine. It's cosine, sine, cosine. So do sine. It's cosine, sine, cosine, past 3 tests, so why wouldn't we do sine?
Okay, so the observation here was that the order was cosine, sine, cosine. It sounds like it's termed. He suggests that it's time for sine.
All right.
So that's so I'm going to do the 2012 problem, which is the sine problem. I'll comment about the cosine, in fact. So the idea for the sine series is that the basic form of the series is this. Coefficient b sub n times the sine n pi over Lx. Now, first of all, L you identify from the statement of the problem. And so if you look at the problems in 2010 and 2011, all right, these come from f of x defined on 0 to L. So for 2010 and 2012, L is 1. That's what's given there. On the 2013 problem, the first one on the list, L is given to be pi. Okay, so that's in effect the first thing that you identify in. So that's the first thing that you identify on this thing is what's L. Right? Now the formula for the coefficients is that it's 2 over L, integral 0 to L, f of x, and the coefficient of the term here is the integral 0 to L of the function times the sine. In terms of if this is the cosine series instead of the sine, well then the cosine goes in here. But it's basically that formula. The one thing about the cosine series, the way I remember the cosine series is that the constant term has a factor of 1/2, and then the integral is exactly the same formula for all values of n. There's a factor of 2 that you got to deal with, one way or another. You remember a separate formula for the coefficient, or you remember that the coefficient is has a 1/2. I remember it this way. That's the way it's in the book. That's the way most of us, but not all, choose to remember the formula. Moving along then to do these things. again for the 2012, I've got B sub n is 2, L is 1, 0 to 1, x up there, L is 1, so x times sine of n pi x dx. And so, how does any reasonable person deal with that integral?
Looking for the integral.
You're looking at a table. All right. So, I can do it by parts, but I'm going to write down the result from the table, although I generated it last night by integrating by parts. So, x sine ax dx, negative 1 over ax cosine ax plus 1 over a squared sine ax. So I have here, there's a 2 outside. A is n pi, right? Just there it is inside the integral. So I have a negative 1 over n pi x cosine n pi x plus 1 over n pi squared sine n pi x. Integral from 0 to 1. At x equal 1, I have a negative 2 over n pi 1 times the cosine of n pi. At n equal 1, there's a sine of n pi, that's 0. At n equals 0, the x in the x cosine ax term gives 0. The sine of 0 is 0. I've got enough room here. And the cosine of n pi is negative 1 to the n over n pi. What's the problem? Let's see, what's the problem asked for? It says find the series. Now, one of the things, if you look at the 2012, it's sort of vague as to what it means by find the series. So certainly a perfectly valid answer, as far as I'm concerned, is that the series is negative 2, negative 1 to the n over n pi sine of n pi x. Okay? In the other two problems, in fact, you are asked to find the first 4 non-zero terms, and so if that had been the request here, I would have started to work my way down the line. Negative 2 n equal 1 is a 2 over pi sine pi x. The next one is going to have a negative 2 over 4 pi sine 2 pi x, putting n equal 2. The n equal 3 term, negative 1 to the third is negative 1 times the 2, so that's got a 2 over 9 pi sine 9 pi x, sine of 3 pi x, excuse me, 3. And the last one has negative 2 over, what am I doing here? I'm squaring things when I'm not supposed to. 2, 3, 4 pi sine 4 pi x, and so on.
What kind of other function would we get for our initial one? Would it be like x squared? Or
But-
would it be like x squared, or would it just have a coefficient in front of it?
One of the kinds of the question was, what other kinds of functions might you expect? The basically, it's not a problem in integration techniques. Therefore, we don't want to make the integration crazy. And so, step functions are kind of a nice example. One example might be to be x from 0 to 1, 0 from 1 to 2. Okay, and so then b sub n, here the function's defined from 0 to 2. So L is 2. It's 2 over 2, 0 to 2, f of x sine n pi x over 2 dx. But now when you put this in from 1 to 2, that's 0. So you get 2 over 2, 0 to 1, x sine n pi x over 2 dx. So a step function, especially a step function where one of the pieces is a 0. So you do that kind of thing.
Okay.
Okay. But not put in x squared. That gets just starts to get a longer function in the table of integrals. I'll still have to draw some pictures. Yes, sir.
If one of them wasn't 0, so then the coefficient would be the two series added together, essentially?
The coefficients would be a sum of two integrals. Sum of two integrals. If this were a 1, then there'd be an integral from 1 to 2 of 1 sine n pi x over 2 dx. I don't know who was first. Yes.
Does the L change since x is
No,
only from 0
the
to
L
1?
comes from the function. If the function here is being defined over this thing, the function that I've just suggested is looks like that. Down here or in the back? Yes, sir.
In the last problem, where does the 1 over n pi squared sine n pi x go?
When at the upper limit at x equal 1, that's a sine of n pi. That's 0. At the lower limit, it's a sine of 0. It's 0. It's when I put the limits on the integration, most of it goes away. The other piece. The other piece of the Fourier series question, it's always in there. Let me come back to you guys in a minute. The rest of what you're asked for on these things is about convergence. The 2012 function, I'm going to deal with do a couple of these. F of x was x, 0 to 1, and it was a sine series. Now, when we ask to what does the Fourier series converge, it starts out, the function's defined on this interval from 0 to L. On the interval from 0 to L, we get the function back. And I'll talk in a moment about one of those examples, not the one I drew, but the other one. We start out with this. Now, the sine series here's my sine series. Every term in the sine series is an odd function, and therefore the series will converge to an odd function. And so the Fourier series from -1 to 1 becomes an odd function. -1 to 1, and in particular it's continuous through this, so I don't have to fuss about things jumping. And now it's odd, and now it's periodic. In general, the period is 2 times L, so the period is 2, and so the problem asked you to sketch this thing from -3 to 3, and the basic idea is that this piece now repeats. So from 1 to 3, I'm going to get this piece from -1 to 1 being repeated. And in particular, here there's a jump, and the Fourier series is a sum of continuous functions. It's going to be continuous. And what these things will do is they'll hit the average at the place where there's a jump. And when I grade this thing, and I like to grade this problem because I like to grade the pictures, which goes very quickly. The pictures either basically right or basically wrong, and it includes the jumps, if any, and take a couple of points off if those jumps weren't marked. Otherwise, look at the thing. So the picture part is easy to do. The previous year's problem. The previous problem, the 2010, had the same function, but a cosine series, and the cosine series again on the basic interval 0 to L will give me the function back, but the cosine series is an even function, and so between -1 and 1, that's going to give me an even function, okay, symmetric across the y-axis, and that will, and this then from -1 to 1, basically from -L to L, gives me my building point on these things, so I repeat that one over and over again. If I had the example that I first put down when the gentleman here said what other kinds of things could be in there, a very sensible question, I thought. And I suggested, for example, this function. That function from 0 to 1 goes up here to x, and then it's 0 from 1 to 2. If I want a sine series, for example, now the Fourier series, here's the jump. The Fourier series is going to converge to 1/2 at the jump point where the function is trying to quickly go from 1 to 0. If it's an odd function, then it has to come down here to -1 from between -1 and 0. And then back to 0 from 1 to 2. Another jump, and now pick that up and repeat it. I'll just draw the one more piece over to the right, okay? So, you start out from 0 to L, there's the function with averages at any jumps, extended, even or odd as necessary because of this cosine or sine, and then from negative L to L, you repeat that left and right.
Do we have to note the averages? Do we have to put a little X at
Put a little X at the averages, yes.
Okay.
As I said, I grade this, okay, I'm up here, I grade this problem, okay, year after year. We each grade certain, Professor Levine and I each have our favorite problem to grade. I'll tell you his in a couple of minutes. He's probably told
That's
you
the
as
PD.
well. Okay, but this is the one I do. And the reason I do it is that it's easy to grade, part of it's easy to grade, which is the picture, and part of the thing that's easy to distinguish between grades is that I look for the points on the jumps. If there are no jumps, like over here there were no jumps, well, okay, that year was even easier to grade.
Professor?
So, moving right along here, what are we doing here on time? 3:45. Yes, sir, Tommaso.
Where are the jumps in that one? On the x-axis? They're at the average from the lowest point and the highest point?
The averages are the jumps here from 1 down to -1, right there.
Okay.
Okay, 1 down to -1. Those are gonna be my jumps. So the thing has,
So-
the thing didn't include the end point.
Cosine won't have jumps at all.
Cosine on this has jumps.
Okay. Okay.
Cosine on this has jumps. Yes, cosine can have jumps.
Okay.
Yes. Yeah. Yes, sir.
What would that one look like if you extended it out further? What would that one look like if you...
See, here's my extension. I repeat this. I did that in a separate color precisely so that I could show you the piece that you pick up and repeat off to the right, same piece off to the left. Okay? I very specifically switched color there to try to help you visualize that. Yes, sir.
When we find the solution of f of x of the, let's say the sine series, do we have to write a few terms? Like 2/5?
The problem will tell you what's wanted. Here, for example, the problem that I particularly picked, the middle one just said find the series. There's the series.
Oh, so you don't really have to write that down.
That's a legitimate answer to that question.
Okay.
Okay? Or you can do it this way, but the other two asked for a certain number of non-zero terms. So there you had to do that.
Thank you.
Now, one of the things that you will see here is, as I'm going through these things, is that there's an example of these kinds of questions on each of these exams, the 2010, 2012, 2013. These are things, and I'm not going to screw around and beat around the bush. There is one of these problems on the exam on Tuesday. There is a series solution problem, an eigenvalue, a Fourier series, in particular the next two things, the last two kinds of things, the separation of variables problem and the boundary value problem for the partial differential equation. Yes, Hudson?
Going back to the last question, how did you come up with the -1 to the n all the way up top?
Cosine of n pi is -1 to the n.
Oh,
Cosine of n pi. I wrote cosine of n pi is -1 to the n. When I evaluated. I put in the values for the Patrick, when I put in the values for x equal 1, x equals 0, x equal 1, negative 1 over n pi, there's a 2 out front. X is 1, cosine of n pi. That's the negative 1. Cosine of n pi, it's right here, cosine n pi, negative 1 to the n. The next thing, the separation of variables problem. This is intended to give you an easy 10, 15 points, 10 points. Yes, sir.
What if it's sine to the n pi, whatever that was, where it was cosine to the n pi,
Sine n pi is 0.
sine to the, it would be pi over n, right?
Pi over n, you just have to leave it there. If it's n times pi over 2, you got to be careful about whether n's even or odd.
So when you're converting to negative 2 to the negative 1 to the n over n pi, what do you do if you have a sine? If it's sine instead of negative 2, or instead of cosine, what would your
Well,
series?
I had a sine term in there, and the sine of n pi was 0. It depends upon what the thing is. If I had, I suggested here, for example, some things which were might end up with things like sine of n pi over 2. That integral from 0 to 1. Well, the sine of n pi over 2 is depends on whether n is even or odd.
Okay.
Okay, and so, and that's the kind of thing that shows up. Those other two problems, the two cosine things, where they were asking you for we asked those students for a certain number of non-zero terms. Those are the kinds of things which show up when there's an n pi over 2 in sine or thing, where sometimes it cancels, sometimes it doesn't. So you get different results depending upon whether n is even or odd.
Okay.
Okay. Some of them cancel, some of them don't. Okay. Something like cosine of n pi. If you get something like cosine of n pi minus 1, so this is alternating between negative 2 and 0.
Okay.
Okay, so those kinds of things happen. So separation of variables. Moving right along, and I need a bit of time for the last problem, not for this one. These things, if you look through these problems on page 3, they are perhaps the most frightening looking problems in the whole exam. And on the other hand, in the second half of the exam, they're the easiest problems, I suggest. It asks you use separation of variables and find two ordinary differential equations. So if I take the one from last year's exam, e to the 2x plus 3t, second partial of u with respect to x and t, minus x plus 4 squared, t plus 7 to the 8th, second partial, t with respect to 0.
It's 4 to the 5th and t squared.
Okay. So basically, we're told that u is a function of x times a function of t is the separation of variable idea. So the partial derivatives, u with respect to an x and a t, that gives a derivative of x times the derivative of t. Second partial with respect to t is x times the ordinary derivative of t. And I'm gonna move the second term to the right-hand side of the equation and start to make things a little more manageable. Exponential of a sum, that's e to the 2x times e to the 3t. The function here, x prime times t prime. On the other side, x plus 4 to the 5th, t plus 7 to the 8th, x times t, second derivative. And now I want everything involving x on one side.
It's x squared on the last term. Then t squared.
Should be t squared
It's
plus
x,
7.
okay, I'm sorry. X double
And it should be t squared plus 7.
t,
And then that is respect to x. And up top it should be partial of x.
X over?
let this with respect to x.
Yeah. There we go.
So it should be X over.
See, you know how to do this better than I do. So I gather everything that involves x on one side. I have e to the 2x, x plus 4 to the 5th, x prime over x double prime. Is t squared plus 7 to the 8t over e to the 3t times t prime. I have perhaps in a screwed up way, but I've got a function of x on the left side, a function of t on the other one. And so those must be lambda. That's the key step, that a function of x equal a function of t has to be a constant. And so the first equation says e to the 2x x prime is lambda x plus 4 to the 5th x double prime, or lambda x plus 4 5th x double prime minus e to the 2x x prime is 0. And the other one has, as I've done it, is t squared plus 7 to the 8t is lambda. Go ahead and move that over move that correctly. I move that over there. Lambda, what? E to the 3t t prime. So I have a lambda e to the 3t t prime minus t squared plus 7 to the 8. T equals 0. So, and that's all that's involved. That's all we want you to do, is to produce that kind of equations. Linking the two, how the constants enter in has to be consistent, but do what's convenient there. I want to rush because I want to spend time on the last problem. So the last problem the last problem here is the full partial differential equation. This is the problem that Professor Levine likes to grade. He likes to grade this for one simple reason. We have found over the years that a significant number of people simply don't do this problem, or yes, a significant number of people don't do this problem. In the past, a significant number of people have not gotten A's in the course. Certainly, our results on the first two exams suggest that there are an awful lot of you who had A's in sight in their sights as possibilities, and therefore my attitude is I would like to make Professor Levine work and grade these problems and have people do well. Okay, now one other thing that you might observe about these exams. Here I actually showed this problems 4 exams back. We had a problem last year which was a heat equation problem. The year before that it was a wave equation. 2012. The time before that it was a wave equation. What do you notice about those two problems?
Same method.
They're exactly the same. We gave the same problem.
So now it's this time.
The results were no better in 2012 than in 2010.
So you're gonna use the same problem next year?
In 2009 we gave a heat equation. So one thing to be said about that is that although it wasn't so much lazy as an experiment to see how things would go if we gave the same problem. We also made a decision that we worked through that. Both of us worked through that problem in class. That we did the whole thing.
This year or that year?
2012. We did the problem in class that was going to be on the exam.
You're gonna do the one that's in the review this time.
Pardon?
You're gonna do the one that's gonna be on the final thing in the review this time.
Well, who knows? It's happened. About 30 years ago, I was doing a review for one of these classes, and the guy said, "Can you do this kind of problem?" I said, "Okay, but I don't have one prepared. Give me one." And he picked one out of the book, which was the problem that was on the final exam. And my thought was that was wonderful. He also got it right, which is the other thing that I wanted to look at. Okay, but about this in particular, aside from the fact that we did exactly the same problem a couple of times, we do, just as with the sines and cosines, we tend to alternate between the two kinds of problems. And so last year was a heat equation. So this year we're due again for a wave equation. So let me do this one for the 2012 exam. Second derivative with respect to x minus 16. Second derivative with respect to t is 0. Boundary conditions. U of 0 and t is 0. U of x, 1 and t is 0. Initial conditions, x and 0 is negative 6 sine 3 pi x over 2 plus 13 sine 11 pi x over 2. And partial derivative with respect to x 0. Okay. So just as with this thing, we start out looking for the separation of variables, writing this as a as a function of x times a function of t. The second derivative with respect to x is the derivative of the x function times t. Partial with respect to t goes the other way. And so we get x double prime t is 16 x times t double prime. X double prime over x is 16 t double prime over t is lambda. First of all, there's a constant in here. The constant in here, this time it happens to be a 16. In general, you want to put the constant with the t. Okay, push it off as long as you can is the basic notion here. So I have x double prime minus lambda x is 0. T double prime minus lambda over 16t equals 0. Pushing the 16 over with as a constant over with the other constant, which is the lambda. And now for the boundary conditions. The boundary conditions apply to x. U of 0 and t is x of 0, t equals 0. That gives me that x of 0 should be 0 for a non-zero solution. I need to have a non-zero solution to generate the initial value. And partial with respect to x at 1 and t is x prime at 1, t of t equals 0. So x prime at 1 should be 0. And so this gives me my an eigenvalue problem. Find those values of lambda such that this differential equation and boundary conditions has a non-zero solution. We have r squared minus lambda is 0. R squared is lambda. And so r is plus or minus square root of lambda. If lambda is positive, I have x is c1 e to the mu x plus c2 e to the negative mu x. X of 0 is c1 plus c2. So c2 is negative c1. X prime mu c1 e to the mu x. C2 is negative c1, negative sign, there's a c1 e to the negative mu x. X prime of 1 is mu, c1 e to the mu plus e to the negative mu equals 0. So c1 is 0, c2 is 0. That one certainly expects. Yes, sir?
Do we have to do all three cases? Because Professor Levine said we only had to do the case with cosines and sines for the exam.
He grades it. If he told you you only had to do the one case, you only have to do the one case.
I think he was just talking about the past exam.
No, he said with 2Ds.
I will tell you, I mean, be precise about one thing. The eigenvalue problem, the standalone eigenvalue problem, just as the one I did, where I did work through the three cases, those are the instructions on those. And certainly you saw double the derivatives on both things. The zero case gave an eigenvalue, so it had to be done. Here the zero case does not, and I want to move through it quickly because it doesn't, it in fact, if you can look at that and say, yes, that doesn't have to be done, so be it, yes. For me, the derivative is always worrisome, but quickly, the zero case gives C1 plus C2x. At 0, it's C1, that's 0. The derivative is C2, and at 1, that has to be 0. So what you say is certainly correct, that those cases don't give any information. Question is, all right, but the case we do have to do certainly is the case that leads to the complex roots, lambda negative. So R is plus or minus mu I, and we get X is C1 cosine of mu X plus C2 sine of mu X. X at 0 is C1 cosine of 0 is 1, C2 sine of 0 is 0. So that's gone. X prime, C1 is gone, so it's C2 mu cosine of mu X. X prime at 1 is C2 mu cosine of mu is 0. I want C2 not to be 0, mu can't be 0, and therefore cosine of mu equals 0 for a non-zero solution. And that occurs when mu is an odd multiple of pi over 2. Right? Odd multiple of pi over 2. 2k plus 1 times pi over 2. 0, 1, 2, and so on. A way to write odd multiples. I'll label that u sub k. Lambda. Lambda is negative mu squared. So negative 2k plus 1 squared, pi squared, 2 squared. And x, corresponding x. The cosine went away. The solutions are coming from the sine. Mu, here's mu. 2k plus 1 over 2 pi x with a constant. All various values of k. Where am I? There. Yep, nonsense. that takes care of X. Next is T up there at the top. Equation for T. Second derivative of T minus lambda over 16T. So here's lambda. There's lambda. Lambda has a negative sign, so this is second derivative plus 2k plus 1 pi. There's a 2. I'm going to put a square here. And the 16 I'm going to write as a 4 squared. Get it in there with the 16, with everything else, equals 0. Everything okay? Did I get the algebra right? Yes, sir.
Wait, when did you get the negative?
There's a negative here and a negative here. Putting in for lambda. Okay? Legitimate question. Okay, so there's my equation for T. And so I can write down the solution for this, for each value of K. The solution to this is sines and cosines of T times that ugly thing inside the square. So I have cosine of 2k plus 1 pi over 8 squared T, and sine 2k plus 1 over 2k plus 1 pi over 8t are the linearly independent solutions. I'll put an A and a B on those.
Why isn't the other one squared?
Why? That one shouldn't be squared. Thank you. Right, that's the case that T double prime plus K squared T equals 0 has solutions cosine of KT and sine of KT. Okay, cosine KT sine. And the T equation comes down, well, you have to work to solve the X equation. The T equation, once you put things in, that falls out. And so I have T, I have X, and I get my formal solution by multiplying the two things together. Now I've got the constants. I've written those constants with capital letters. I'm going to switch to they get multiplied by the C's. So I can write this at maximum ugliness now. A sub k cosine 2k plus 1 pi over 8t sine 2k plus 1 pi over 2x plus b sub k sine 2k plus 1 pi over 8t sine 2k plus 1 pi over 2x. I'm writing a sub k, lowercase, as ck, ak, capitals. Okay, to get rid of that. Oh, okay. So that's as ugly as, that's pretty ugly. So let's see if we can start to simplify. We've got two things left, which are the initial conditions. Zeros are generally easier to deal with than non-zeros. So So I'm gonna head for this u sub t of x and 0. I need a u sub t on this thing. U sub t, sum. Well, I said that I was about maximum ugliness. I take it back. This is uglier. Partial derivative with respect to t. That's going to pull out a 2k plus 1 pi over 8. So I get a sub k negative sine 2k plus 1 pi over 8t sine 2k plus 1 pi over 2x plus b sub k cosine 2k plus 1 t sine over 8t sine 2k plus 1 pi 2x. Close it. So the initial conditions, let me write them from what I'm concerned with down. It's that at x equals 0, x equal x, t equals 0, I get 0. U sub t at x and 0. To infinity, 2k plus 1 pi over 8. T equals 0. This goes away. This goes away. B sub k, the cosine of 0 is 1 times the sine, 2k plus 1 pi over 2x. That has to be 0. And therefore all the b's are 0. The other initial condition is in terms of u at x and 0. So now in terms of u at x and 0, the second part of that is gone, of my solution. I end up with k equals 0 infinity. A sub k, set t equals 0, the cosine of 0 is 1. Sine of 2k plus 1 pi over 2x. And that should be, reading from the problem, negative 6 sine 3 pi over 2x plus 13 sine 11 pi over 2x. And so, all the terms here are of this form. These are just two of the terms here. The first one corresponds to k equal 1. When k is 1, I get 3 pi over 2 inside the sign. So A1 is negative 6. This corresponds 11 pi over 2. That corresponds to k equal 5. So A5 is 13. All the other A sub k's are 0. And so I finally end up with a solution. U is equal to A1, negative 6, and I've got to pick up this cosine thing. cosine over 8, I'm going to have a sine of 3 pi over 2x. It's 3 pi over 8t. The other one is the 13, cosine 11 pi over 8t, sine 11 pi over 2x. So it ends up with a simply matching term by term here. Now, if you look, and that's the kind of problem that we put on the exam every year, which is on the exam on Tuesday.
This problem.
Yes, sir, Adam.
Are you guys gonna leave like extra paper in there for us to write? So like right now, just one sheet of paper.
Well, the exam, if I remember it, is 18 pages.
How many are blank?
You've got not only the front but the back. Okay, that gives you 36 sheets, 35 sides, not the front page. Let me just say one thing. If you carry something over onto the other side, if you carry it over to the back of a different page, put a note at the bottom. Please turn over. Please go to back of page 7. Wherever it is. There are, in my opinion, only a couple of problems which should require you to go to the back of the pages. Okay.